Hello and welcome to another video on forces. Specifically, we're going to start talking about systems, and in this video, two-wire problems. One of the eventualities of dealing with physics is that it's going to start getting a little more complicated. For instance, in this problem, we have a chandelier, a poorly drawn chandelier, but a chandelier nonetheless, hanging from the ceiling. And as it hangs, one of the questions that will come up is, what's the tension in these two wires up here? Where's the tension here and here? We could also ask about wire 3, but that one's fairly easy. Now, this problem depends on knowing what the mass of the chandelier is. So let's say this chandelier is 25 kilograms. Once we know this mass, we can start drawing free body diagrams. The first is the easiest. Let's draw one for the chandelier itself. Do that in red. So the chandelier has force gravity pulling it down, and that tension force pulling it up. And because the chandelier is hanging in space, or standing still, we know that this force and this force have to be equal. So whatever the tension is, will be the force gravity. Or in other words, and that's easy, that's simple. But wires 1 and 2 prove to be slightly more problematic. Because once you get here, the tension gets split. And it's not exactly evenly split either. The burden of bearing this tension here falls on these two strings combined, but there's also the left-right forces. And what we end up doing is we end up adding a coordinate system to this. And instead of drawing the free body diagram for a single object, what we end up doing is drawing it for a point, the center point right here. Because at this point, all the forces are acting, and they're acting directly on this point. If we look at the free body diagram for this specific point, we have tension 2 pulling up and to the right, tension 1
pulling up and to the left.
and tension 3 pulling down.
And since the hanging chandelier isn't moving, all three of these forces have to add up to 0.
So if I write my sum of all forces for the x direction, for instance, sum of all forces x, T2 is pulling to the right and T1 is pulling to the left. So my T1 in the x direction minus my T2 in the x direction have to balance out, have to equal 0. If I do the same thing for this point in the y direction, let's go ahead and erase this, we'll keep the fact that force tension 3 equals m times g of the chandelier. I have that force tension 1 and force tension 2 are pulling up, but force tension 3 is pulling down. And again, this will be equal to 0 because it's not moving, the chandelier is just hanging there. Putting little y labels on here to indicate y direction as opposed to x direction. And from here, the question of what is the tension becomes solvable, well, provided you know the angles. Because then all you have to do is plug in your angles, solve them out, and, well, split your tensions into T1y and T1x and T2y, T2x. Now, we think we have a lot of unknowns and such, but we can simplify it down to terms we know. For instance, if I focus over here, I know that T1 in the y direction over T1, opposite and hypotenuse sides, will equal sine of my angle. Or in other words, T1y equals Ty sine theta. I can do the same thing for T1x and get T1x equals T1 cosine theta. And then over here, the same thing for T2. T2x equals T2 cosine. I'm going to use a different variable. I'm going to use phi to indicate that they're not the same angle. Do the same thing for y. And if I plug these values in, and substitute mg in for force tension 3, I know my angles, I know my mass, and I know g. So all that's left is to solve for the unknown, or more accurately, solve for both unknowns. Because we have two equations, two unknowns, we can end up with what's called a system of equations. You're probably familiar with this from math, the simpler idea of what we're about to do, but it's the same process. We can do it symbolically or plug in our numbers. Whatever works, all we need to do is rearrange one of these equations to solve for one variable and then plug into the other. And that's the general principle for any systems problem. Draw a free body diagram, write sum of all forces expressions for both free bodies, and then combine until you run down to a number of equations equal to your number of unknowns. Here, let's finish this one off. It doesn't matter which one you do. You can do T1 or T2. I'm going to solve for T1 just because. And now that I have this, and whenever I see T1, I'm going to plug it in over here. So 0 equals T1, which is actually T2 cosine phi over cosine theta times sine theta plus T2 sine phi minus mg. And from here, it's just a matter of solving out the equation, getting T2 by itself. Let's take that to the next page. I can plug in my numbers right now and solve. I'm going to continue doing this symbolically. If you want to do numbers, I'll show that over here after pause. But solving symbolically, I need to get T2 by itself. So let's get the mg to the other side. T2 will factor out, and then divide to the other side. At which point I can just plug in my numbers. My mass is 25. G is 9.8. Cosine of phi, I said, was 20. Sine of 45 over cosine 45 plus sine 20, which, put that all together, type it in your calculator. And this will tell me that T2 is 191.15 newtons. I'm going to pause here, put in the work on the other side, and we'll come back. Now that's not the end. Unfortunately, we have T2, but we need to go back and plug into T1. Thankfully, we have an expression for that. We said that T1 equals T2 cosine of phi over cosine of theta. Or in other words, T2, which is the 191 we just found, times cosine of 20 over cosine 45, which equals 254.02 newtons. And that's how you solve a two-wire problem. Just write down your equations, and eventually it'll end up being a system of equations, much like this. If you can't do the symbolic solve, do the numerical one. It works out. A typical question for one of these would be like, if we use wires that are rated up to 300 newtons, will they break? Or if we have a 300 newton rated wire, what angle does it need to be at? In general, solve the problem normally from that point, and then compare your numbers. Let's put one more up here as an example. A wrecking ball has been stored away for the night. It's stored such that the wires are set up like so. what I want to know is where the tension's in the wire while it's at rest. A thing to note that this is perfectly in the x direction. And number two, we're going to assume that the wires are taut. This is a common assumption because it means that the tension is uniform or close to uniform throughout the wire. Dealing with non-uniform tension and non-uniform wires is a problem beyond the scope of this class, but just so you know the terminology. Go ahead, give this a try on your own. Check back when you're done. Okay, here we go from the top. I wrote down my sum of all forces x, my sum of all forces y. You'll notice this is a little simpler because T2 is only in the x direction. For T1x minus T2 will equal 0, and T1y minus mg will equal 0. I set this up to solve. I could have gotten the number right here and plugged it in, but I decided to take this entire expression and plug it in to my red expression for the x direction to show how the system of equations would work. I solved both. I get 4,477.55 newtons, with the decimal a little clear there. For T1, and for T2, I get 2,878.11 newtons. Anyways, thanks for watching. Have a good day.